Somewhere between light and time, the Milky Way carries the memory of everything that has ever been. Its stars are older than language, its dust older than the oceans, and its spiral arms stretch across 100,000 light-years like a frozen wave in eternity. Tonight, we'll travel through that wave, past the clouds of creation, the fossils of starlight, and the quiet arithmetic of cosmic age, to uncover a secret billions of years in the making. How old is the galaxy that gave birth to our sun, and what does its age say about our place in the universe? Like and subscribe if you enjoy journeys through space and wonder. It helps us reach more dreamers. Let's begin. Beneath the darkness, the Milky Way glows like a soft river of light, each droplet a star, each current a story billions of years long. But this river isn't flowing through space, it's flowing through time. If you've ever stood beneath a clear, moonless sky and seen that faint, misty band stretching from one horizon to the other, you've already glimpsed the body of our galaxy. What looks like a cloud is actually the combined light of more than 400 billion suns, so distant that their glow blends into a single silvery shimmer. Each point in that glow is separated from the next by unimaginable distances, trillions of miles of quiet vacuum. And yet together they form something whole, a slow-turning spiral that has been drifting through the universe for nearly the entire history of time itself. For centuries, we thought the Milky Way was all there was. To ancient astronomers, it was the spine of the night sky, the path of the gods, the smoke of creation. Only in the last 100 years did we learn that this glowing band is one galaxy among billions, and that ours stretches 100,000 light-years wide, its arms curling gracefully like a frozen whirlpool of stars. Each orbit of this spiral, each revolution of its suns, takes more than 200 million years to complete. While humans rise and vanish in the blink of a cosmic eye, the galaxy barely shifts, turning endlessly in its slow celestial waltz. But what we see when we look up is not the galaxy as it is now. Light takes time to travel, and that faint shimmer we admire tonight left those stars thousands, even tens of thousands, of years ago. In every direction, the Milky Way is a time machine, showing us ghosts of light from the distant past. The farther we look, the older the memory. The edge of the galaxy, faint and remote, shines from an era when early humans were carving stone tools beneath unfamiliar skies. From our small world, this river of stars seems eternal, but it too had a beginning. Every glimmer is born from gas and gravity, each star igniting in a cradle of dust, living for millions or billions of years, then dying in brilliance to seed the next generation. The Milky Way is not a static sculpture. It breathes, it recycles, it remembers. Through it flows the same atoms that once blazed inside earlier stars, the same particles that now live in our blood and bones. We are, in a very real sense, droplets within this river, carried along by its current through time. When we gaze at the Milky Way, we are seeing the history of everything that ever was, layer upon layer of starlight stacked through eternity. It is a gentle reminder that even in the vastness, nothing is truly lost. Every atom finds its way back into the flow. Every light eventually returns to the stream. The galaxy is not just a collection of stars, it is a living river, and we are part of its endless tide. Long before Earth existed, a cloud of hydrogen began to collapse under gravity's patient pull. Out of that collapse came rotation, pressure, and the first spark of galactic life. The universe was still young then, dark, cooling, and newly born from the energy of the Big Bang. The first atoms drifted through an endless night, forming vast, invisible oceans of hydrogen and helium that stretched for millions of light years. There were no stars yet, no galaxies, no light at all, just gravity, quietly gathering the raw materials of creation. Over hundreds of millions of years, these cosmic tides began to clump together, pulled by tiny fluctuations in density left behind by the birth of the universe. Where the gas was slightly thicker, gravity pulled harder, and the first great clouds began to fall inward on themselves. Within those collapsing clouds, something extraordinary began. As gravity compressed the gas, it heated. Hydrogen atoms, once spread thin across space, were forced together until the first stars flared into being. Bright hot giants that burned through their fuel in only a few million years, the universe, once silent, was suddenly ablaze. Their light tore through the darkness, turning the cosmos from an opaque fog into a luminous expanse. Those early stars didn't live long, but they left behind something priceless. Heavier elements forged in their fiery cores: carbon, oxygen, iron, gold. When they exploded as supernovae, those elements scattered across space, enriching the surrounding gas and setting the stage for new generations of stars. Out of these cycles of birth and death, the first protogalaxies emerged. They were far smaller and rougher than the graceful spirals we know today, more like chaotic swarms of stars and gas colliding and merging in the dark. Each merger gave the system more mass, more gravity, and more spin. Slowly, over billions of years, the Milky Way began to take shape, its central bulge forming first, dense and bright, while a halo of ancient stars spread outward like a cosmic cocoon. Eventually, the young galaxy found balance. Gas flattened into a rotating disk, spinning faster as it contracted, until great spiral arms unfurled, patterns formed not by the stars themselves, but by waves of density moving through the disk, like ripples across a pond. The Milky Way's structure was born, a brilliant core surrounded by elegant, rotating arms filled with the promise of new suns. It's humbling to think that all of this happened billions of years before the sun ever rose, before Earth's oceans shimmered under starlight. Our galaxy's birth was not an event, but a slow unfolding, gravity's art performed over cosmic time. From chaos came order. From darkness came light. And from that first luminous breath of hydrogen and fire came the home that now holds us all, drifting quietly among its hundreds of billions of stars. When we look up at the Milky Way tonight, we're not just seeing a galaxy. We're witnessing an ancient masterpiece still in motion, painted across the fabric of time itself. The earlier stars of the Milky Way were massive, unstable, and short-lived. They burned through their fuel in a cosmic heartbeat, dying in explosions that seeded the newborn galaxy with light and metals. Before these titans were born, the universe was cloaked in shadow. For hundreds of millions of years after the Big Bang, space was filled with darkness, an ocean of invisible hydrogen, silent and cold. Then, gravity began to sculpt light. Within the densest knots of gas, hydrogen atoms collided and fused, releasing the first photons that pierced the cosmic night. The darkness didn't vanish all at once. It shimmered, rippled, and slowly began to glow as the first stars awakened. These first suns were unlike anything that exists today. They were enormous, hundreds of times more massive than our sun, and burned with fierce blue-white light. Their gravity was immense, their energy violent. They lived fast and died young, lasting only a few million years before collapsing under their own weight. When they died, they didn't fade gently. They erupted as supernovae, scattering heavy elements across the void in waves of radiant debris. Each explosion was both an ending and a beginning. The light they unleashed illuminated space for the first time, and the matter they expelled became the seeds for everything to come: planets, moons, oceans, and life itself. Iron from their hearts would one day beat inside human blood. Carbon from their ashes would form the molecules of thought. The universe, once simple and pure, now contained complexity, a chemistry capable of memory. As these first stars died, they left behind black holes and neutron stars, dense remnants that continued to shape their surroundings. The gas and dust they expelled cooled and gathered again, forming new generations of stars, each one slightly richer in elements than the last. With every cycle, the galaxy grew more diverse, more structured, more luminous. The Milky Way was learning to build itself. If we could watch this epoch unfold, we would see light blooming across the cosmos like fireflies in a growing dawn. The first stars turn the night translucent, their ultraviolet radiation ionizing the surrounding hydrogen, transforming the opaque fog of the early universe into the clear space we see today. This era, when the universe first learned to shine, is known as the cosmic dawn. It was the moment the lights came on in the universe, and the darkness began to dream of form. Every star in the night sky is a descendant of those first celestial beacons. Their brilliance echoes in the light we see now, faint but eternal. When you look up and trace the band of the Milky Way, remember that its glow is the language of those first fires, the moment when darkness found its voice and the universe began to tell its story in light. Before the spiral arms formed, there was a halo, a rough, spherical swarm of ancient stars still circling the galaxy today. These stellar elders whisper the first chapters of our origin. Long before the Milky Way became the graceful spiral we see now, it was a cloud of chaos, turbulent, uneven, full of collisions and raw energy. Out of that primordial disorder emerged the halo, a vast sphere of stars and clusters that wrapped around the young galaxy like an old memory. It was the first architecture of the Milky Way, a relic from an era when gravity worked with the patience of eternity, pulling the first stellar systems into shape. The stars of the halo are ancient beyond comprehension, more than 13 billion years old, nearly as old as time itself. Many are small, dim red dwarfs that have burned steadily since the universe's youth. Others are found in globular clusters, dense, shimmering balls of hundreds of thousands of stars packed into regions only a few dozen light-years across. These clusters orbit far above and below the galactic disk, their paths slow and stately, tracing ellipses carved by gravity billions of years ago. To astronomers, the halo is a time capsule. By studying the light from its stars, they can read the early chemical history of the galaxy. Most of these stars contain almost no heavy elements, only hydrogen and helium, with traces of lithium. They were born before the Milky Way's first supernovae had time to enrich space with metals. Their simplicity is their story. They carry within their spectra the fingerprints of the universe before complexity began. The halo also reveals how the Milky Way grew. Its stars don't orbit in neat circles like those in the spiral arms. Instead, they move in tilted, looping, and chaotic paths, evidence of ancient mergers with smaller galaxies long since absorbed. Every captured star, every scattered cluster, became part of the halo's diffuse glow. It is, in a sense, cosmic archaeological layer, an amalgam of countless ancestral galaxies blended into one. Even now, new evidence shows that the halo continues to evolve. Streams of stars, remnants of dwarf galaxies torn apart by gravity, thread through it like veins of light. One of them, the Sagittarius stream, is a ghostly reminder that our galaxy is still growing, still consuming its neighbors, still reshaping its edges. The halo holds both the oldest and the newest arrivals, a living record of everything the Milky Way has been and is becoming. If the bright spiral arms are the galaxy's face, then the halo is its memory. It watches quietly from above and below, unbothered by the chaos of star birth and death in the disk. Its stars move slowly, as though time itself thickens there. When you look up and see the faint glow of the Milky Way, remember that around it drifts an invisible sphere of ancient light. Stars so old they have seen nearly the entire story of creation unfold, still circling, still keeping watch over the spiral that came after them. Every element in a star tells time. By reading the abundance of iron, magnesium, and carbon, astronomers can trace not just where a star was born, but when. In the silence of space, there are no calendars, no ticking clocks. Yet every atom carries a memory, a kind of cosmic timestamp etched into its chemistry. Stars, like living things, are products of their environments, born from the matter available at a particular moment in cosmic history. The very elements that compose them serve as clues to their age, allowing astronomers to reconstruct the galaxy's long and intricate biography. When the first stars ignited billions of years ago, the universe was simple, composed almost entirely of hydrogen and helium, with only the faintest traces of lithium. There were no heavy elements yet, no oxygen to breathe, no carbon for life, no iron for worlds like ours. These primordial stars lived fast and died in spectacular explosions, scattering their newly forged elements into the interstellar medium. With each new generation of stars, the gas grew richer, more complex, infused with the remnants of its predecessors. The cosmic chemistry evolved, and in that evolution, time left its mark. Astronomers measure this progression using what they call metallicity, the proportion of elements heavier than hydrogen and helium in a star's atmosphere. A star with very little metal content likely formed early in the galaxy's life, before many supernovae had occurred. A star rich in metals must be younger, born from gas that has been recycled and enriched by countless stellar generations. It's a beautiful symmetry. The death of one star gives birth to another, and in the ratio of their elements, time itself can be measured. Certain elements act as more precise markers. Iron, for instance, builds up over long timescales, primarily produced in the slow death throes of smaller stars. Magnesium and oxygen, by contrast, form quickly in massive stellar explosions. Comparing the ratios of these elements allows scientists to estimate how many generations of stars had already lived and died when a particular star was born. It's like examining the growth rings of a tree, each layer of enrichment marking another chapter in the galaxy's unfolding story. Using these stellar fingerprints, astronomers have mapped the chemical history of the Milky Way. They've discovered that the oldest stars, those in the halo, contain almost no metals, while younger stars in the galactic disk carry the signatures of long chemical refinement. Some even show patterns unique to smaller galaxies that were later absorbed, proof of the Milky Way's cannibalistic past. Every measurement adds another piece to the puzzle, a new tick on the cosmic clock. When we gaze at the night sky, the light we see is ancient, but the chemistry behind it is older still. Each photon carries information about the world that produced it, what it was made of, when it was born, and what came before. To study the stars is to read the universe's autobiography, written not in ink but in iron and carbon. The galaxy itself is a clock, and we are learning to listen to its steady chemical heartbeat. Every element in a star tells time. By reading the abundance of iron, magnesium, and carbon, astronomers can trace not just where a star was born, but when. In the silence of space, there are no calendars, no ticking clocks. Yet every atom carries a memory, a kind of cosmic timestamp etched into its chemistry. Stars, like living things, are products of their environments, born from the matter available at a particular moment in cosmic history. The very elements that compose them serve as clues to their age, allowing astronomers to reconstruct the galaxy's long and intricate biography. When the first stars ignited billions of years ago, the universe was simple, composed almost entirely of hydrogen and helium, with only the faintest traces of lithium. There were no heavy elements yet, no oxygen to breathe, no carbon for life, no iron for worlds like ours. These primordial stars lived fast and died in spectacular explosions, scattering their newly forged elements into the interstellar medium. With each new generation of stars, the gas grew richer, more complex, infused with the remnants of its predecessors. The cosmic chemistry evolved, and in that evolution, time left its mark. Astronomers measure this progression using what they call metallicity, the proportion of elements heavier than hydrogen and helium in a star's atmosphere. A star with very little metal content likely formed early in the galaxy's life, before many supernovae had occurred. A star rich in metals must be younger, born from gas that has been recycled and enriched by countless stellar generations. It's a beautiful symmetry. The death of one star gives birth to another, and in the ratio of their elements, time itself can be measured. Certain elements act as more precise markers. Iron, for instance, builds up over long timescales, primarily produced in the slow death throes of smaller stars. Magnesium and oxygen, by contrast, form quickly in massive stellar explosions. Comparing the ratios of these elements allows scientists to estimate how many generations of stars had already lived and died when a particular star was born. It's like examining the growth rings of a tree, each layer of enrichment marking another chapter in the galaxy's unfolding story. Using these stellar fingerprints, astronomers have mapped the chemical history of the Milky Way. They've discovered that the oldest stars, those in the halo, contain almost no metals, while younger stars in the galactic disk carry the signatures of long chemical refinement. Some even show patterns unique to smaller galaxies that were later absorbed, proof of the Milky Way's cannibalistic past. Every measurement adds another piece to the puzzle, a new tick on the cosmic clock. When we gaze at the night sky, the light we see is ancient, but the chemistry behind it is older still. Each photon carries information about the world that produced it, what it was made of, when it was born, and what came before. To study the stars is to read the universe's autobiography, written not in ink but in iron and carbon. The galaxy itself is a clock, and we are learning to listen to its steady chemical heartbeat. In 2014, scientists found a star called SMSSJ 031366708, born just 100 million years after the Big Bang. It's a living relic older than our galaxy's spiral arms. This star, faint and unassuming through a telescope, is one of the most extraordinary discoveries in modern astrophysics. SMSSJ 031366708, located roughly 6,000 light-years away in the constellation Hydrus, belongs to a population so ancient that it bridges the gap between the first generation of stars and all those that came after. It is a fossilized ember from an era when the universe was still learning to create structure, a survivor from the time when the Milky Way itself was still forming from loose gas and dust. What makes this star remarkable is its metallicity, or rather, its near absence of it. Astronomers define metals as any element heavier than hydrogen or helium, and in SMSS J031366708, the amount of iron is less than 1/10,000,000th that of the Sun. That level of purity indicates it was born from matter that had been touched by only a single supernova, one of the first to ever explode in the young universe. The composition of this star provides a rare glimpse into the conditions that prevailed before galaxies were mature, before the cosmos was enriched by the countless cycles of stellar death and rebirth. By analyzing its light with high-resolution spectroscopy, scientists identified delicate traces of carbon, magnesium, and calcium, elements likely dispersed by a relatively gentle first-generation supernova, one that didn't completely scatter its outer layers into space. This subtle enrichment allowed a new star to form from the cooled remnants, a second-generation star that has endured for over 13 billion years. Its very existence is a clue that the first stars were not all colossal and destructive. Some left behind material calm enough to birth long-lived stars like this one. SMSS J031366708 has remained stable for eons. Small, cool, and efficient, it burns its hydrogen with incredible restraint, ensuring it will likely outlive our Sun by trillions of years. To observe it is to look backward through time, nearly to the beginning. Its light, ancient and unbroken, carrying within it the story of the universe's infancy. Each photon from this star has crossed epochs, from the cosmic dawn through the birth of galaxies, past the rise of the Milky Way's spiral arms, and finally into the lens of modern telescopes. When astronomers point their instruments toward it, they are not simply studying a star, they are reading a fragment of cosmic scripture. SMSS J031366708 reminds us that even in a universe governed by impermanence, there are survivors of extraordinary endurance. It is a quiet, steadfast witness to everything that followed: the formation of galaxies, the birth of solar systems, the awakening of life, and somewhere in its steady glow lies a profound truth, that the light we see tonight was kindled at a time when the universe itself was still finding its shape, when creation was new and the future was only beginning to dream itself into being. Most of the Milky Way's oldest stars orbit far above and below its shining disk. In the silent halo, a region that holds the clues to how galaxies first assembled. If the luminous spiral of the Milky Way is its face, the halo is its hidden history, an immense, invisible sphere surrounding the galaxy, filled with ancient stars, ghostly streams, and the quiet residue of long-vanished worlds. To the naked eye, it's unseen, but to astronomers, it's one of the richest archaeological archives in the cosmos, a time capsule of how the Milky Way grew from chaos into grace. Stretching hundreds of thousands of light years in every direction, the halo is sparse yet immense. Its stars are scattered like embers drifting away from a long-cooled fire, faint, isolated, but enduring. Many of them are among the oldest known, born more than 13 billion years ago, before the Milky Way even had a defined structure. Their orbits are not confined to the galaxy's flat plane. They loop and tilt in every direction, tracing paths carved by gravity during the Milky Way's earliest mergers. These stars are survivors of collisions, their movements like fossils preserved in motion. For decades, astronomers thought the halo was just a random cloud of old stars. But deeper surveys, like those from the Gaia spacecraft, have revealed its secret. It isn't random at all. Hidden within the halo are streams and shells of stars, coherent patterns that wind through the darkness like fingerprints of ancient collisions. Each stream marks the remains of a smaller galaxy that once ventured too close and was torn apart by the Milky Way's gravity. These shredded systems, their stars flung into vast arcs, now orbit invisibly through the halo, telling the story of cosmic cannibalism on a galactic scale. One of the most famous of these remnants is the Gaia Enceladus sausage, a poetic name for a long-ago collision. Roughly 10 billion years ago, a smaller galaxy, about a quarter the mass of the Milky Way, was absorbed into our own. Its stars, flung into elongated, sausage-shaped orbits, now make up much of the inner halo. The merger helped puff up the Milky Way's early disk, stirred its gas, and sparked new waves of star formation. The halo, once thought to be a static relic, is now understood as the debris field of our galaxy's violent youth. The halo also hides something even more mysterious: dark matter. Invisible and silent, it outweighs the visible galaxy by a wide margin, forming a gravitational cocoon that holds everything together. The halo's motions, its unseen mass, reveal the presence of this dark skeleton, the unseen structure that gives galaxies their form and fate. So when you imagine the Milky Way glowing gently across the night sky, remember that it is wrapped in an unseen ocean of ancient light and invisible mass. The halo is both our oldest ancestor and our quiet guardian. It remembers every collision, every birth, every borrowed star. Within its stillness lies the secret of how galaxies grow, and perhaps how they endure. The Milky Way wasn't always alone. Over billions of years, it devoured smaller galaxies, absorbing their stars and mixing their ages into its vast body. In the silent stretches of cosmic time, galaxies are not the static, peaceful islands we once imagined. They are predators and survivors, shaped by collision and consumption. Gravity is the sculptor of the universe, but it is also its appetite. It pulls galaxies together, stretches them apart, and eventually merges them into something larger, something more complex. The Milky Way, for all its serene beauty, is no exception. Beneath its calm spiral lies a history of violence, a story written in the orbits of stars that once belonged to other worlds. Astronomers now believe our galaxy has consumed dozens of smaller companions since its birth. These galactic meals began in the earliest epochs, when the universe was young and galaxies were small. The Milky Way's gravity lured nearby dwarfs into its growing halo, their stars torn loose like sparks from a fire. Each collision left behind faint traces, streams of stars wrapping around the sky, remnants of galaxies devoured long ago. Some of these streams are still visible today, like scars in the darkness. marking where entire star systems were once alive. The most famous of these ancient mergers is the Gaia-Enceladus event, a cataclysmic collision that occurred around 10 billion years ago. When the Milky Way absorbed this smaller galaxy, the impact reshaped our own structure, thickening the disk, scattering stars into the halo, and giving birth to new generations of stars. The chemical fingerprints of those foreign suns still linger, distinct in their metallic makeup. To this day, astronomers can tell which stars were born here and which came from elsewhere simply by reading their light. And the feast didn't end there. The Sagittarius dwarf galaxy, for instance, is currently being torn apart as it orbits us, its stars stretching into long, glowing rivers across the sky. The Magellanic Clouds, two smaller satellite galaxies visible from the southern hemisphere, are destined to meet the same fate in the far future, their matter gradually absorbed into the Milky Way's vast disk. What looks tranquil from our perspective is, in truth, a slow-motion act of cosmic assimilation. This process of galactic cannibalism is not cruelty, it's creation. Every merger enriches the Milky Way, blending new stars, elements, and motions into its structure. Without these collisions, our galaxy would be smaller, dimmer, and chemically poorer. Even our Sun, and perhaps the very material that formed Earth, may owe their existence to such ancient unions. The Milky Way's complexity, its billions of stars and intricate spiral design, is the result of billions of years of gravitational hunger. When you look up at the glittering band of the Milky Way, you're not seeing a single entity, but a tapestry woven from many lives, each thread a galaxy that once shone alone. In the grand rhythm of the cosmos, destruction and creation are the same act. The Milky Way's elegance was carved by its appetite, and every star that burns today is a testament to what it has consumed and what it has become. A river of stars arcs across the sky, a shredded remnant of a galaxy torn apart by our own. It's proof that the Milky Way grows not just by birth, but by consumption. High above and below the familiar spiral of our galaxy flows a faint, silvery current of light known as the Sagittarius stream. It winds across the heavens in a vast, graceful loop that wraps around the Milky Way like a celestial ribbon, nearly encircling it. To the unaided eye, it's invisible, hidden behind veils of dust and distance, but to telescopes, it glows like the soft echo of a vanished world. This stream is all that remains of the Sagittarius dwarf galaxy, a once independent system now being slowly devoured by the Milky Way's relentless gravity. The Sagittarius dwarf galaxy first fell into our galaxy's gravitational grip billions of years ago. What followed was a slow, graceful act of cosmic destruction. Each time it swung around the Milky Way, tidal forces stretched it thinner, pulling its stars into long, flowing arcs. Over countless orbits, the smaller galaxy was torn apart completely, its stars now scattered into two great streams that wrap around us from pole to pole. The process continues even today, as new stars are stripped away, joining the galactic tide that flows invisibly through our night sky. Astronomers first detected the Sagittarius stream in the 1990s, when careful surveys revealed stars moving in peculiar orbits that didn't match the rest of the galactic disk. They were outsiders, foreigners traveling through our starfield on paths that told a story of capture and dissolution. With modern mapping from the Gaia spacecraft, scientists have traced this stellar river in exquisite detail, confirming that it wraps around the Milky Way more than once. It's not just a remnant, it's a living record of an ongoing merger, still unfolding in slow motion. Every star in the Sagittarius stream carries a different accent of light, a slightly different chemical signature, revealing its true origin. Many are older and less metal-rich than those born in the Milky Way, confirming they were forged in a smaller, simpler galaxy. Some even orbit backward relative to our spiral arms, proof of the chaotic choreography of galactic evolution. The Milky Way has absorbed many such companions over time, but the Sagittarius dwarf is special because we are witnessing its end firsthand, a galaxy dissolving into ours before our very eyes. Through this process, the Milky Way grows. Each stolen star adds to its mass, Each disrupted orbit reshapes its structure. Even the gravitational waves of the collision ripple through our galaxy's disk, stirring new regions of star formation. What may seem destructive is, in truth, a form of creation, a recycling of matter and light into new beginnings. The Sagittarius stream is a quiet reminder that the night sky is not static. It's alive with motion, with the slow dance of galaxies merging and transforming across eons. The stars that now blend seamlessly into our Milky Way were once part of another world, another story. And though that galaxy has been torn apart, its memory flows forever in the river of light that circles our own. A stellar testament to how the universe grows, not by peace, but by beautiful, patient ruin. By studying stellar ages and motions, scientists reconstruct the Milky Way's family tree. Each orbit, each metallic signature, is a clue to a long-forgotten merger. Every star is a record keeper, a glowing artifact from a specific moment in cosmic history. Its color, composition, and motion all tell a story, if you know how to read it. In that way, astronomers have become something like archaeologists, digging not through soil and stone, but through space and time. Instead of fossils, they unearth ancient light. Instead of pottery shards, they study stellar spectra. The field is called galactic archaeology, and through it, we're beginning to piece together the epic saga of how the Milky Way became what it is today. To practice galactic archaeology, scientists collect light from millions of stars and break it apart into its component colors using spectroscopy. Each element absorbs light at specific wavelengths, leaving behind thin, dark lines in a star's spectrum, a chemical fingerprint that reveals its ancestry. Older stars, formed when the galaxy was still young, show fewer of these lines. Younger stars, born from gas enriched by countless generations of supernovae, display a more intricate spectrum. By reading these spectral patterns, astronomers can estimate a star's age, birthplace, and even which long-lost galaxy it might once have belonged to. But chemistry is only half the story. The other half is motion. With data from missions like Gaia, scientists have mapped the positions and velocities of over 1 billion stars in our galaxy. When plotted together, these motions reveal hidden structures, streams, clusters, and vast, looping orbits that betray the Milky Way's violent past. Some groups of stars move together through space with a shared chemical signature, proof that they were once part of the same ancient dwarf galaxy before being consumed. These stellar migrations are the fossils of galactic evolution, preserved in the geometry of the sky. Through this cosmic detective work, astronomers have reconstructed a surprisingly complex lineage. The Milky Way is not a single, uniform structure. It's a mosaic built from many smaller galaxies. Ancient collisions with systems like Gaia Enceladus, Sequoia, and Helmi stream left lasting imprints in both chemistry and motion, each event adding new stars to the halo, bulge, or thick disk. Every orbit tells a chapter, every chemical ratio a sentence. Piece by piece, the family tree of the Milky Way emerges, rooted in the early universe and branching into the spiral arms that cradle our sun. What makes galactic archaeology so profound is that it connects us directly to that ancient story. When scientists analyze the light of nearby stars, they're reading the biography of our cosmic home, decoding how long-forgotten collisions built the very environment that allowed Earth to exist. It's an act of remembrance written not in words, but in starlight. The next time you look up at the Milky Way, imagine it not as a single, smooth river of stars, but as a layered history, a cathedral built over billions of years, each stone laid by the merging of worlds. Galactic archaeology reminds us that even in the vast stillness of space, the past is never truly gone. It shines above us, quietly waiting to be read. The very first stars, called Population 3, no longer exist. But their fingerprints remain in the next generation, locked in trace elements scattered across space. Long before the Milky Way took form, before the spiral arms and nebulae, the universe was dark and simple, an ocean of hydrogen and helium left behind by the Big Bang. For hundreds of millions of years, this vast fog drifted, cooling and condensing under the pull of gravity. Then, at last, the first lights ignited. The first generation of stars was born, and the age of illumination began. These pioneers, the population 3 stars, were nothing like the ones we see today. They were titans, hundreds of times more massive than our Sun, burning at temperatures so intense that they lived for only a few million years. Their light was the universe's first language, searing through the primordial darkness and ending the cosmic night. But their lives were brief and ferocious. When they died, they exploded as supernovae, scattering the first heavy elements into space: carbon, oxygen, iron, and more. From those ashes, all future stars, planets, and eventually life would be built. None of these original stars survive today. They burned themselves out eons ago. But their existence is written into the chemistry of everything that followed. The second generation of stars, population 2, formed from the gas enriched by those first explosions. When astronomers study their light, they find faint but unmistakable traces of the elements the first stars forged. It's like finding a fingerprint pressed into the dust of creation, a subtle residue that says, "We were here first." Modern telescopes like James Webb and Hubble are searching for the faint glow of that era, the moment when the first stars ignited. Though they're too distant and ancient to see directly, their presence can be inferred through their influence, the way they re-ionized hydrogen, the way they shaped the early galaxies, the way they seeded the cosmos with the building blocks of complexity. Each bit of data brings us closer to witnessing the first sunrise of the universe. In many ways, we owe everything to those vanished stars. Every atom of oxygen we breathe, every speck of gold, every drop of iron in our blood, each was born in their furnaces. When you hold a coin, when you take a breath, when you look up at the Milky Way, you are touching the relics of those first celestial fires. They are gone, but their legacy is everywhere. The first generation of stars taught the universe how to shine. Their light was brief, but it transformed everything. They gave the cosmos color, chemistry, and story. In their deaths, they made it possible for others to live, and in that sense, they are not gone at all. Their memory glows in every star that came after, including the one that warms our own small world. What we call cosmic dust isn't debris, it's memory. Every grain once lived inside a dying star, then drifted through eons before helping to form planets like ours. When we hear the word dust, we think of something ordinary, something forgotten, something to be brushed away. But in the vastness of space, dust is sacred. It is the raw material of existence, the ashes of stars that have lived and died across billions of years. These tiny particles, silicates, carbon, ice, and metal, float between the stars, glimmering faintly in the cold light of distant suns. They are the universe's storytellers, carrying within them the entire chemical history of creation. Every grain of cosmic dust begins its journey in the heart of a star. As stars age, they fuse lighter elements into heavier ones, filling their cores with carbon, oxygen, and silicon. When the most massive among them explode as supernovae, these newly forged elements are cast into space, where they condense into microscopic crystals and mineral grains. Even gentler stars, like our Sun, create dust when they die, expelling their outer layers into colorful nebulae that slowly cool and solidify into fine, drifting matter. In this way, the death of one generation becomes the foundation of the next. These grains travel across the galaxy, drifting for millions, sometimes billions, of years. They are pulled into molecular clouds, cold, dense regions where new stars and planets are born. There, gravity gathers them together, clumping dust into pebbles, pebbles into rocks, and rocks into worlds. Every planet, moon, and asteroid began as dust. Even you did. The calcium in your bones, the iron in your blood, the silicon in your cells, all of it once floated between the stars as part of this cosmic cycle. To astronomers, dust is not just a symbol, it's a tool for understanding. Infrared telescopes like James Webb can peer through thick dust clouds that hide newborn stars, revealing the structures of stellar nurseries and the first glimmers of planet formation. When scientists collect meteorites that fall to Earth, they sometimes find tiny grains older than our Sun, presolar dust, formed in the atmospheres of stars that died before our solar system even existed. To hold one is to touch something older than our world, a relic of the galaxy's earliest ages. Cosmic dust also softens the universe's light. It scatters and absorbs radiation, creating the gentle glow we see in nebulae and the faint haze that outlines the Milky Way. It's as if the galaxy itself is veiled in memory, wrapped in the remnants of all that has come before. Without dust, the sky would be brighter, but emptier. So the next time you see sunlight catch a floating speck in your room, imagine this. That particle's story began long before humanity, long before Earth, perhaps inside a star that burned when the galaxy was young. What we sweep away so casually is, in truth, the dust of creation, ancient, enduring, and endlessly reborn. At the Milky Way's center lies Sagittarius A star, a supermassive black hole around which everything orbits. But its own age tells a story of growth and violence stretching back 13 billion years. It is the quietest point in our galaxy, and its most powerful. Hidden behind clouds of dust and gas, Sagittarius A star sits in the constellation of Sagittarius, about 26,000 light-years from Earth. It is 4 million times more massive than our Sun, yet smaller than the orbit of Mercury. Space bends around it like glass around a flame. Nothing that crosses its boundary, the event horizon, can ever return. And still, this immense darkness anchors the entire Milky Way, holding hundreds of billions of stars in its gravitational embrace. For much of history, the center of our galaxy was a mystery. Ancient stargazers saw the dense band of light across the night sky, but could never have imagined the monstrous calm that lies at its core. It wasn't until the late 20th century that astronomers, tracking the motion of stars near the center, realized something extraordinary must be there, an invisible mass so concentrated that only a black hole could explain it. The stars closest to Sagittarius A star move at speeds exceeding 5,000 kilometers per second, completing orbits in mere years. Their dance reveals what the eye cannot see, a singularity hidden beneath veils of starlight and shadow. But Sagittarius A star is not an ancient relic frozen in time. It's a dynamic survivor, the product of billions of years of cosmic history. The Milky Way likely began with a smaller black hole, formed from the collapse of a massive star in one of the galaxy's earliest generations. Over eons, as the galaxy grew through collisions and mergers, that black hole feasted, consuming gas, dust, and entire stars drawn too close. Each act of destruction fed its growth, transforming it from a stellar remnant into a supermassive giant. In a sense, Sagittarius A star is the memory of every catastrophe the Milky Way has ever endured. Astronomers studying its emissions have discovered that it's not as dormant as it seems. Occasionally, Sagittarius A star flares, brief bursts of X-ray light that may be caused by magnetic storms or the shredding of unlucky asteroids falling toward its maw. And deep radio observations reveal filaments and waves near its event horizon, relics of a more active past when it may have blazed like a quasar, pouring energy into space. Even now, faint echoes of that ancient fury ripple through the surrounding gas. The age of Sagittarius A star cannot be pinned down with precision, but clues from simulations and stellar archaeology suggest it began forming not long after the Milky Way itself, perhaps over 13 billion years ago. It has watched the galaxy grow, evolve, and transform around it, remaining steady while everything else moves. It is the axis of our existence, the silent center of our cosmic spiral. And yet, though it devours light, it also gives shape to the galaxy's beauty. Without Sagittarius A star, the Milky Way would not hold together as it does. The stars, nebulae, and planets, including our own, move in harmony because of its unseen pull. It is the paradox of creation. From the heart of darkness, structure emerges. So when you look toward the center of the Milky Way, through dust, distance, and time, you are looking toward the galaxy's oldest memory. It reflects not light, but gravity, time, and the unending balance between destruction and creation that defines the universe itself. At some point, chaos became symmetry. Gas clouds flattened, gravity sculpted spiral arms, and the galaxy began to turn like a celestial whirlpool frozen in motion. The Milky Way wasn't always the graceful spiral we see today. In its earliest age, it was a storm of disorder, clumps of gas, dark matter, and newly formed stars colliding and merging in a turbulent sea. Gravity was the great composer of this chaos, pulling material inward while rotation began to bring balance. Slowly, almost imperceptibly, the chaos began to find rhythm. As the growing galaxy accumulated more mass, angular momentum, its inherited spin from the motions of early collapsing gas began to assert itself. Clouds of hydrogen and helium, once moving in every direction, started to align along a common plane. Each rotation pulled the gas a little flatter, a little tighter, until the young Milky Way began to resemble a vast, rotating disk. The same physics that flattens a spinning pizza dough or a whirlpool in water now shaped an entire galaxy. Within that disk, the seeds of structure began to emerge. Dense regions of gas collapsed to form new stars, their birth sending waves of energy and pressure rippling through the surrounding medium. Those ripples became the first hints of spiral arms, patterns of compression that swept through the disk like sound waves through air. Contrary to what we might imagine, the spiral arms aren't fixed structures made of the same stars forever. They're density waves, areas where stars and gas bunch together as they orbit, glowing brighter for a time before moving onward. It was in this era, roughly 10 to 11 billion years ago, that the Milky Way found its shape. The central bulge formed first, a dense cluster of old stars bound tightly to the galaxy's heart. Around it, the disk expanded and spun, fed by rivers of infalling gas and the debris of smaller galaxies it had absorbed. Over hundreds of millions of years, symmetry deepened. The spiral pattern became more distinct. The galaxy learned to rotate as one vast, coherent being. Even now, the Milky Way continues to spin, its outer edges completing a full revolution roughly every 230 million years. That means since the dinosaurs walked the Earth, our solar system has traveled around the galaxy's center only once. With each turn, stars rise and fall through the galactic plane like dancers following a cosmic rhythm. A silent choreography that has been ongoing for billions of years. The moment the disk began to spin was more than a change in structure. It was the birth of grace from chaos. The universe had found balance in motion, beauty in symmetry. From that turning came the spiral arms that cradle nebulae, the pattern that guides star formation, and the galactic rhythm that still carries us through the night sky. When we look up and trace the Milky Way across the heavens, we are seeing the frozen swirl of that ancient dance, a galaxy forever in motion, yet perfectly still to our eyes, like the crest of a wave caught in the act of becoming. Using the motion of stars and radioactive isotopes, astronomers calculated the Milky Way's age, about 13.6 billion years, nearly as old as the universe itself. Time behaves differently on a galactic scale. It doesn't tick in seconds or minutes, but in the slow revolutions of stars and the fading light of isotopes that have been decaying since the dawn of everything. The Milky Way, our quiet spiral of existence, carries within it the cosmic equivalent of a clock, a set of natural mechanisms that allow scientists to measure how long it has been turning in the dark. The most ancient parts of the galaxy, its halo and globular clusters, hold the first clues. Globular clusters are dense, spherical gatherings of hundreds of thousands of stars, some so old that they contain almost no heavy elements. By comparing their brightness and color to stellar models, astronomers estimate that many of these clusters are around 13 billion years old. Since they likely formed soon after the Milky Way began to assemble, their ages provide a lower boundary for the galaxy itself. But astronomers don't just rely on starlight. They also use the atoms within those stars as natural timekeepers. Certain radioactive isotopes, such as thorium-232 and uranium-238, decay at known and incredibly steady rates. By measuring the relative amounts of these elements and their decay products within old stars, scientists can determine how long those isotopes have been fading, much like reading the half-burned wick of a candle. The results consistently point to the same conclusion. Our galaxy formed roughly 13.5 to 13.6 billion years ago, just a few 100 million years after the Big Bang. That means the Milky Way is nearly as old as the universe itself, a first-generation structure in the grand architecture of creation. It began taking shape while the cosmos was still thick with hydrogen fog, when light had barely traveled across the first million light-years. Its oldest stars, fossils of that early era, still orbit in the halo today, moving like ancient hands on an invisible clock face that has been turning since time itself began. Even motion can be a measure of age. By studying the speed and paths of stars around the galactic center, astronomers can estimate how long the Milky Way has been rotating as a cohesive system. One complete orbit of the disk takes about 230 million years, so in its 13.6 billion year lifetime, the galaxy has turned roughly 60 times. Every rotation is a tick of the galactic clock, each one marking another epoch of cosmic change. When you stand beneath the Milky Way and see its faint arc stretched across the sky, you are witnessing the frozen face of this immense timepiece. Its stars, its dust, even its gravity, all of it has been aging in unison since the beginning. And though billions of years have passed, the galaxy still spins, still creates, still measures time in the quiet language of light and decay. We often think of clocks as things that count down, but the Milky Way's clock counts up, marking not an end, but a continuity. Every pulse of radiation, every orbit of a star, is a reminder that time is not just something we pass through. It's something the universe keeps, faithfully, in every grain of stardust and every turn of the spiral. In human terms, the Milky Way's lifetime is unimaginable. It has watched entire civilizations rise and vanish before a single galactic year has passed. If our galaxy had a heartbeat, it would pulse once every 230 million years, the time it takes for our solar system to complete one full orbit around the galactic center. In that vast span, continents drift, mountains crumble, and species emerge and disappear, all while the Milky Way makes just one slow turn in the darkness. The galaxy moves with a serenity that only time itself can teach. To it, the entire history of human civilization, every empire, every discovery, every fleeting age, has happened in less than the blink of an eye. The stars do not hurry. They burn at their own pace, unconcerned with the small urgencies of the worlds that orbit them. When we measure time in minutes and hours, the cosmos measures in billions of years. It's a patience so deep it almost feels divine, a quiet endurance that humbles everything we know about change. The Milky Way has existed for 13.6 billion years. In that time, stars have lived and died, galaxies have collided and merged, and still, the spiral continues to turn, graceful and slow. Our solar system joined this grand rotation only 4.6 billion years ago. To the galaxy, we are latecomers, children born long after the music began. And yet, from our perspective, it feels like eternity. Every night, we look up at the same ribbon of light that ancient humans saw, and we imagine it as still. But even now, the stars are moving, the arms are breathing, the galaxy is changing, so slowly that no single lifetime could ever notice. Astronomers often say the universe has infinite patience. Stars form from collapsing clouds that take millions of years to condense. Planets cool for eons before life stirs. Even light itself takes tens of thousands of years to escape from a star's core. Everything in the cosmos happens on timescales that defy human comprehension. Our entire existence, every heartbeat, every story, unfolds between the faintest ticks of the galactic clock. And yet, within that smallness lies beauty. The fact that we can look up and understand even a fraction of this vast, slow dance is extraordinary. The Milky Way doesn't rush to become, It simply is, and in its patient turning, it allows time enough for beings like us to rise, wonder, and reflect. It teaches us that creation isn't about speed, but endurance. When you look into the night sky and feel the weight of its stillness, remember that you are witnessing an ongoing masterpiece billions of years in the making. The stars have waited this long for your eyes to find them. They will wait longer still, burning quietly, turning endlessly, carrying within them the reminder that even the universe, so vast, so old, moves not with haste, but with perfect, cosmic patience. Cosmic background radiation still lingers, the afterglow of the Big Bang. Against it, the galaxy's faintest stars look almost modern, born long after the first light cooled. Cosmic background radiation still lingers, the afterglow of the Big Bang. Against it, the galaxy's faintest stars look almost modern, born long after the first light cooled. Long before the Milky Way began to form, before the first stars ignited or galaxies spun, the universe glowed with a soft, uniform light. It was not the light of stars or fire, but of pure energy, remnants of creation itself. This ancient radiation, known as the cosmic microwave background or CMB, is the oldest light we can see, the faint afterimage of the moment the universe became transparent. Every direction we look, this glow surrounds us, stretched thin by billions of years of cosmic expansion. It is the universe's first whisper, still echoing across eternity. About 380,000 years after the Big Bang, the young cosmos cooled enough for protons and electrons to combine into neutral hydrogen. In that instant, light, previously trapped in a fog of charged particles, was finally free to travel. Those first photons began their long journey, crossing expanding space for more than 13.8 billion years to reach us today. As the universe grew, their wavelengths stretched, fading from visible light into the faint microwave radiation astronomers now detect with sensitive instruments like Planck and WMAP. The result is a perfect snapshot of the universe's infancy, a cosmic baby picture etched into the very fabric of space-time. To the human eye, this light is invisible, but its faint hum fills every corner of existence. Even the static between radio frequencies contains its echo, a soft residue of the universe's birth. And when scientists map the CMB, they see subtle ripples, tiny variations in temperature, just millionths of a degree, that mark the first seeds of structure. Those slight differences are what gravity later amplified into galaxies, clusters, and, eventually, the Milky Way itself. By the time our galaxy began to take shape, around 13.6 billion years ago, this primordial light had already been shining for hundreds of millions of years. The CMB became the background against which the universe's next act unfolded, the first stars flaring into being, forging the heavy elements that would one day form planets and people. Compared to that ancient afterglow, even our oldest stars are newcomers, their light flickering across a sky already illuminated by memory. In a way, the cosmic microwave background is a cosmic boundary, a horizon of time beyond which we cannot see. It marks the limit of the knowable past, the final remnant of a time when matter and energy were one. To study it is to touch the first moment the universe could see itself, when light first escaped the fog and began to tell the story we now inhabit. And so, when we gaze into the night and see the Milky Way arching across the sky, its starlight shimmering softly through darkness, we are seeing layers of time stacked upon time. The faintest photons from the CMB, born before any galaxy existed, still pass through us. The newest starlight from the Orion Arm mingles with the oldest radiation in the universe. It's all one continuum, light that began with the birth of everything. Still traveling, still telling the story of how the dark learned to shine. Faint, dim companions orbit the Milky Way like lost memories, remnants of the first galaxies ever formed, still drifting at the edge of our gravity. Far beyond the Milky Way's bright spiral arms lies a vast, near-invisible wilderness, the galactic halo. Within that emptiness float dozens of small, ghostly galaxies, each one a survivor from the universe's earliest days. They are faint, ancient, and fragile. dwarfs in every sense, their light so dim that many remained undetected until just a few decades ago. Yet these quiet companions are more than curiosities. They are living fossils of the cosmic dawn, tiny islands of stars that preserve the universe as it once was. These dwarf galaxies orbit the Milky Way in long, looping paths, some taking billions of years to complete a single revolution. The two brightest, the Large and Small Magellanic Clouds, are visible even to the naked eye from the southern hemisphere, glowing like soft lanterns in the night sky. But beyond them, dozens more lurk in the darkness, galaxies so faint they hold only a few thousand stars. They are called ultra-faint dwarfs, and they are among the oldest and most pristine stellar systems ever found. Their stars are ancient, metal-poor, and sparse, unchanged since nearly the beginning of time. Many of these tiny galaxies stopped forming new stars billions of years ago, leaving behind stellar populations that have been burning quietly ever since. Studying them is like peering into the fossil record of the cosmos. Their chemical signatures match those of the universe's earliest epochs, giving astronomers clues about how the first galaxies formed and how they interacted with the growing Milky Way. The most intriguing thing about these ghost galaxies is that they shouldn't have survived at all. When the Milky Way grew through mergers and collisions, most small galaxies were shredded, their stars flung into the halo as tidal streams. But a few somehow endured, too small to destroy completely, too remote to be absorbed. They now linger at the very edge of our gravitational reach, orbiting like ancient satellites around a much larger world. Some may still be slowly unraveling, their stars drifting into the Milky Way's outer halo, becoming part of its ever-expanding family. Modern telescopes like Gaia, Subaru, and the Dark Energy Survey continue to uncover new members of this faint entourage. Each discovery redraws the Milky Way's outskirts, revealing a web of tiny companions linked by gravity and history. Some of these dwarfs, like the recently discovered Crater 2, are so diffuse that if you place them in the night sky, they would stretch wider than the full moon, but they are so dim you'd never see them. These ghost galaxies remind us that the universe keeps its oldest secrets not in brightness, but in silence. They are the quiet witnesses of creation, drifting slowly through the dark, untouched by time. And though their light is faint, their story glows brightly in the Milky Way's shadow, a testament to endurance, memory, and the gentle persistence of the first galaxies that ever dared to shine. Not all stars are ancient. The youngest ones glow blue and hot in the spiral arms, reminders that our galaxy, though old, is still alive and making new suns. If you look closely at the Milky Way, you can see time itself written across its face. The galaxy is not one age but many, an immense mosaic of generations layered upon one another. In the halo, the oldest stars burn faint and red, survivors from the dawn of creation. Closer to the spiral arms, young, brilliant stars blaze in blues and whites, their light so intense it washes out the subtler glow of their elders. Together, they form a living gradient of time, a celestial family album stretching across 100,000 light-years. Each region of the Milky Way tells a different story. The halo is ancient, its stars low in metals and high in age. The bulge near the center contains older stars as well, crowded and reddish, born in the galaxy's youth when gas and dust were abundant but chaotic. But in the disk, especially in the spiral arms, new stars are born every day. Here, the galaxy's rivers of gas compress under gravity, collapsing into glowing nurseries like the Orion Nebula and the Carina Nebula. Within these vast clouds, pressure and heat ignite nuclear fusion, and new suns are born, surrounded by swirling disks of dust that may one day form planets. The color of a star reveals its age. The bluest ones are the youngest and the most short-lived, massive, bright, and destined to burn out in just a few million years. Yellow stars, like our Sun, are middle-aged, stable for billions of years before slowly dimming into red giants. And the faint red dwarfs, which make up the majority of the galaxy's population, can live for trillions of years, longer than the universe has even existed so far. Together, they form a stellar ecosystem in constant motion, creation and decay intertwined. By studying the ages of stars across different regions, astronomers can map how the Milky Way evolved over time. The outer disk is younger, still forming stars, while the inner disk and bulge have largely gone quiet. This gradual aging gives the galaxy its structure and rhythm, a cycle of renewal that has continued since its birth 13.6 billion years ago. Despite its immense age, the Milky Way is not fading, it's breathing, pulsing with the steady rhythm of creation. Our own Sun is a product of this long process of galactic recycling. It formed about 4.6 billion years ago, from gas enriched by countless earlier generations of stars. The carbon in our bodies, the calcium in our bones, the oxygen in our lungs, all were forged in older suns that lived, died, and returned their elements to the galaxy's great workshop. We are, quite literally, the children of stellar time. So when you gaze at the Milky Way and see its glowing arms stretching across the night, remember, you're looking at a portrait painted in ages. Some of those lights are ancient embers, others are newborn flames, and together they whisper a simple truth, that even in its old age, the galaxy is still alive, still dreaming, still making new stars to replace the ones that fade. Elements like iron and gold didn't exist at the galaxy's birth. They were forged in the deaths of countless stars, each explosion marking another tick of cosmic time. At the beginning, the universe knew only simplicity. Hydrogen, helium, and a trace of lithium drifted through the void, the most basic ingredients for light, but not for life. The first stars burned these primordial gases into heavier elements, and when they died, they seeded space with their ashes. Those ashes, carbon, oxygen, iron, and beyond, became the letters of a new language, the chemical story of time. Every atom heavier than hydrogen is a witness to something that once lived and died in fire. The oxygen we breathe was born in the cores of massive stars, fused from helium under crushing pressure. The calcium in our bones formed in supernovae, scattered across the galaxy in waves of glowing debris. Even the gold in a wedding ring traces its ancestry to cataclysms rarer and more violent still, the collision of neutron stars, where gravity and radiation combine to forge the heaviest elements in a heartbeat. Each of these events left behind not just matter, but a timestamp. The more metals a star contains, the longer the galaxy has been alive, accumulating the dust of generations. In that sense, the Milky Way's chemistry is its calendar. The earliest stars, the ancient, metal-poor ones in the halo, speak of a time when the galaxy was young, still learning to create. The next generations, richer in iron and carbon, mark the rise of supernovae and the slow spread of stardust through the disk. Today, stars like our Sun contain traces of nearly every element known to science, each one a record of billions of years of cosmic recycling. The galaxy has become a chemist, blending and refining, turning the raw light of the Big Bang into the complexity of planets, oceans, and thought. Astronomers can read this story directly from starlight. Using spectroscopy, they separate a star's glow into bands of color and measure the absorption lines created by each element. Every dip in the spectrum is a word in the language of time, revealing what the universe had to work with when that star was born. In this way, scientists have built a kind of cosmic timeline, showing how the Milky Way matured from a simple, metal-poor cloud into the rich, life-bearing galaxy we inhabit today. It's humbling to realize that the elements we take for granted are not eternal. They were made, one by one, in the furnaces of stars that lived and died long before the Earth existed. Every breath, every heartbeat, every thought relies on atoms that were forged in explosions billions of years ago. We are the continuation of that chemistry, living proof that time, given enough patience, can turn chaos into consciousness. So the next time you touch something cold and metallic, remember that you are holding the ashes of stars, the memory of their brilliance preserved in solid form. The galaxy keeps time not in seconds or centuries, but in elements, each one a mark on the long scroll of cosmic history, a story still being written in every flicker of light across the Milky Way. Every atom in your body was once inside a star that lived and died before the sun existed. When you breathe, you are inhaling the galaxy's autobiography. It's one of the most astonishing truths in science, one so profound that it blurs the line between physics and poetry. You are made of the same matter that once blazed in stellar hearts, that drifted for billions of years through the cold dark before gathering again into the fragile miracle of life. Every breath you take, every cell you grow, every thought that sparks in your mind is built from atoms that were forged in the furnaces of ancient suns. You are not beneath the stars, you are of them. Consider the journey of a single atom of carbon in your blood. It may have begun inside a massive star more than 10 billion years ago, compressed in its fiery core as hydrogen fused into helium, and helium into heavier elements. When that star reached the end of its life, it exploded, scattering its contents across the galaxy. The carbon atom drifted for eons, caught in shock waves, frozen in dust, bathed in light, until it found itself inside a cloud of gas that would one day collapse to form our sun and its planets. Eventually, it became part of the Earth. The same is true for the calcium in your bones, the iron in your blood, the oxygen you breathe, the phosphorus that powers your cells. Each element is a chapter in a story that began long before humanity, before Earth, before even the Milky Way's spiral arms had found their shape. You are, in a literal and cosmic sense, a continuation of the galaxy's evolution. A collection of atoms that learned how to look back at the stars and recognize themselves. When astronomers say we are stardust, it's not a metaphor, it's a measurement. The proportions of elements in your body match those produced by generations of stars: oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, iron. The iron that helps your blood carry oxygen was born in the violent death of a supernova. The oxygen you inhale came from a star much like our sun. Even the tiny amounts of gold and copper in your tissues were created when two neutron stars collided somewhere in the distant cosmos, long before the solar system existed. What makes this realization so humbling is not just that we come from the stars, but that we will one day return to them. Every atom in our bodies is on loan, destined to be recycled again and again. The carbon we exhale as breath will become part of the air, the oceans, the rocks, and eventually, perhaps, part of another world, another life. In time, all that we are will drift back into the galactic sea, waiting for the next act of creation. So when you stand beneath the night sky and feel the quiet pull of wonder, remember, you are not a spectator in this story. You are a sentence in the galaxy's autobiography, written in stardust and breath. You are the universe, aware of itself, shining, thinking, and remembering what it once was. In the Orion Arm, vast nebulae like the Eagle and Carina are still giving birth to stars. These regions are the galaxy's way of remembering how to begin again. Even in its old age, the Milky Way is far from quiet. Across its spiral arms lie enormous clouds of gas and dust, cosmic wombs where gravity, chemistry, and light conspire to create something new. These stellar nurseries are among the most beautiful and dynamic places in the universe. They glow in soft hues of red and blue, shaped by winds from young stars and sculpted by shockwaves from ancient ones. In these drifting clouds, the galaxy practices its oldest art, the making of stars. The Orion Nebula, only about 1,300 light-years away, is one of the most active of these nurseries. Even with the naked eye, you can glimpse it as a faint blur in Orion's sword, but through a telescope, it comes alive, billowing gas illuminated by newborn suns, their light reflecting off curtains of dust that stretch for dozens of light-years. Within this single nebula, thousands of stars are forming, each surrounded by disks of gas and rock that could one day become planets. Some of those worlds may already exist, quietly orbiting their new suns beneath swirling veils of cosmic light. Farther out lies the Eagle Nebula, home to the famous Pillars of Creation, towering columns of gas and dust photographed in breathtaking detail by the Hubble and James Webb telescopes. These pillars are the skeletons of a dying cloud, eroded by radiation from nearby massive stars, even as new stars are born inside them. It's a paradox written in light, destruction and creation unfolding side by side, the galaxy's eternal balance between ending and beginning. The Carina Nebula, one of the largest in our galaxy, tells a similar story on an even grander scale. It spans over 300 light-years and contains some of the most massive and luminous stars ever found. Giants that live fast and die young, flooding their surroundings with fierce winds and ultraviolet radiation. Their energy stirs the cloud, triggering new waves of star formation. One generation gives rise to the next, and in this ongoing cycle, the Milky Way renews itself, keeping its heart young. Every star we see in the night sky was once born in a nebula like these. Our Sun, too, began in such a place about 4.6 billion years ago, likely alongside hundreds of sibling stars that have since scattered across the galaxy. The dust that formed Earth, and everything upon it, was forged in that same kind of cradle, a reminder that life itself is a continuation of this galactic nursery's work. When we look at these luminous clouds through modern telescopes, we are not merely observing distant scenery, we are witnessing the act of creation as it still happens today. The Milky Way, ancient and vast, continues to make new stars, as if to remember its own beginnings, as if to whisper to the darkness that the story is far from over. In these nebulae, we glimpse the patience of the cosmos, the quiet persistence of a galaxy that never forgets how to begin again. In 4 billion years, the Milky Way will merge with Andromeda. Two ancient galaxies, nearly the same age, will dance together and become one. At first glance, the Andromeda galaxy seems impossibly far away, a faint smudge of light in the northern sky, visible only under the darkest conditions. Yet it is our cosmic twin, a majestic spiral almost identical to our own, and it is moving toward us at a speed of over 100 kilometers per second. The space between us is not empty, it's shrinking. In the deep future, the two great spirals of our local group will collide, their arms intertwining in a slow, graceful waltz that will last for billions of years. The word collision might sound violent, but in truth, the event will unfold more like a dance than a crash. The vast distances between stars mean that very few will ever actually strike one another. Instead, their collective gravities will weave the galaxies together, stretching them into elongated shapes, flinging long tidal tails of stars into intergalactic space, and triggering waves of star formation as gas clouds compress under the strain. It will be a spectacle of unimaginable beauty, two spirals merging into one luminous, transforming form. Simulations show that as the galaxies approach, their disks will first brush past one another, creating immense arcs of starlight that stretch for hundreds of thousands of light years. Over time, they'll fall back together, their cores spiraling inward, until finally, after several passes, they fuse. The Milky Way and Andromeda will no longer be two separate entities, but a single, larger galaxy. An elliptical system astronomers have already named Milkomeda. For our solar system, the collision will be an extraordinary event, but not an apocalyptic one. By then, the Sun will be nearing the end of its life, swelling into a red giant. The night sky, however, will be spectacular. Future observers, if any remain, will see Andromeda grow larger with each passing eon until it fills the heavens, its spiral arms glowing across the firmament. Eventually, the two galaxies' stars will blend into a vast, shimmering sea of light. This merger will reshape not only the galaxies themselves, but also the gravitational choreography of our entire region of space. The Milky Way and Andromeda, along with the smaller Triangulum galaxy, will likely form the core of a new, massive galactic system, one that will drift together for trillions of years as the universe continues to expand. And in a poetic way, this coming union is the final step in a long story. The Milky Way was born from mergers, built by collisions that shaped its spiral beauty. The encounter with Andromeda will be both an ending and a beginning, a return to the process that created us. The galaxies will not die, they will transform. 4 billion years from now, Long after the last of our cities have crumbled and our sunlit world has faded, the Milky Way's light will still be reaching out, and Andromeda will be reaching back. Their dance will continue in silence, two ancient spirals joining hands beneath the cold eternity of space, merging not in destruction, but in creation. Age isn't measured in years, but in the ratios of elements, in orbits, in radiation decay. When we speak of the Milky Way being 13.6 billion years old, it's easy to imagine a number ticking upward, like the seconds on a clock. There are no calendars in space, no sunrise or sunset to mark the passing of days. Instead, the galaxy measures its life in quieter ways, in the fading of light, in the distribution of metals, in the decay of atoms that have been slowly whispering their secrets since the dawn of creation. Its memory is written in mathematics, not motion. The Milky Way's history is preserved in ratios, subtle relationships between elements that change as stars live, die, and give their ashes back to space. For example, the amount of iron compared to hydrogen tells astronomers how many generations of stars have burned before a new one formed. The ratio of uranium to thorium in a star's atmosphere acts like a radioactive clock, counting down from the universe's earliest moments. Even the presence of certain isotopes, like europium and neodymium, tells scientists when and where the heavy elements were born, whether in the heart of supernovae or the collisions of neutron stars. Each measurement, each equation, adds another layer to our understanding of time's true scale. To a physicist, age is a pattern, not a moment, a mosaic of evidence drawn from the chemistry of stars, the motion of clusters, the temperature of radiation, and the expansion of space itself. In these patterns, the Milky Way reveals its patience. Every decay, every rotation, every photon emitted is a quiet arithmetic of existence, balancing energy and matter across billions of years. The galaxy's orbits also keep time, though their pace is glacial. The Sun, for example, moves at nearly 230 kilometers per second around the galactic center, completing one revolution roughly every 230 million years. That means since life began on Earth, the solar system has circled the galaxy about 20 times. Dinosaurs appeared, flourished, and vanished before we even finished one. To the Milky Way, these ages are fractions of seconds in a grand, eternal equation. Even the cosmic background radiation, the faint afterglow of the Big Bang, serves as a chronometer. As it cools and stretches with the expanding universe, it tells us precisely how long it has been since everything began. The galaxy doesn't measure this in emotion or memory. It measures in temperature, in wavelength, in ratios that never forget. And yet, there's something deeply human about this silence. The Milky Way doesn't need to know its age, it is its age. Every atom, every star, every orbit holds the sum of all that has come before. To exist within it is to move through an unbroken chain of time so vast that it humbles every human measure. We mark years, the galaxy marks patterns. We celebrate moments, it sustains cycles, and somewhere between our heartbeat and its rotations lies the truth of time itself, not as a ticking clock, but as a memory, softly repeating through light, gravity, and dust. Stars move like notes on a grand cosmic score. Their oscillations, spins, and orbits let astronomers date the movements of our spiral to its first symphony. If the Milky Way could be heard instead of seen, it would sound like music, an intricate harmony of motion and gravity composed over billions of years. Each star plays its part in this silent symphony. Some move in slow, sweeping orbits, others drift with erratic grace, and together they form rhythms that tell the story of a galaxy in constant motion. To astronomers, this motion is more than beauty. It's data, a language through which the Milky Way reveals its age, its structure, and even its origins. Every star in the galaxy moves under the same gravitational field, yet no two follow exactly the same path. Some trace elegant circles around the galactic center, like dancers following a gentle melody. Others move on tilted, looping trajectories that carry them above and below the disk, their patterns shaped by past collisions and the invisible pull of dark matter. These motions aren't random, they are memory. A star's orbit remembers where it was born and what forces shaped it. The halo's elongated paths whisper of ancient mergers, while the spiral arm's smoother flows hum with ongoing creation. Astronomers have learned to listen to this cosmic music through a field called galactic dynamics. Using instruments like the European Space Agency's Gaia spacecraft, scientists have measured the positions and velocities of more than 1 billion stars. When plotted together, these movements form patterns, streams, ripples, and oscillations that act like musical motifs repeating across the galactic score. Some of these waves were likely caused by past encounters, perhaps the Sagittarius dwarf galaxy brushing through our disk, sending a resonant vibration through millions of stars. Others may be the echoes of even older collisions, still rippling after billions of years. This symphony of motion doesn't just describe the present, it reveals time itself. By modeling how stars move and accelerate, astronomers can calculate when the Milky Way's structures formed. The rate of rotation in the disk tells us when it settled into its spiral shape. The distribution of stellar orbits helps trace the ages of different galactic components. The bulge, the thin disk, the thick disk, the halo, each layer moves to its own rhythm, its own tempo in the grand performance of creation. Even our Sun is part of this orchestra. It orbits the galactic center at about 230 kilometers per second, bobbing gently up and down through the plane of the disk every 30 million years. As it travels, it carries Earth and all of us through an ever-changing landscape of stars and nebulae. To think that our entire history, from the first humans to this moment, has occurred during just one small fraction of a single orbit, is to realize how vast and patient the galaxy's song truly is. The Milky Way's motion is silent to our ears, but its harmony is everywhere, in the swirl of spiral arms, in the drift of starlight, in the gravitational balance that holds everything together. To study its music is to hear the universe thinking, to recognize that even amid the emptiness, there is rhythm, pattern, and grace. The galaxy's first symphony began almost 14 billion years ago, and even now, its notes are still unfolding, echoing softly through the dark, infinite concert hall of space. Every layer of the Milky Way, from halo to bulge to disk, preserves a geological record of time, carved not in stone, but in starlight. If a geologist could read the galaxy instead of the Earth, they would find strata just as clear, each one recording a different epoch of cosmic history. But instead of sediment and fossils, these layers are made of stars, gas, and motion. Frozen moments of evolution, built up over 13.6 billion years. The Milky Way is not a single structure. It's a time capsule, with every region holding a chapter of its past. The oldest layer is the halo, a vast, spherical cloud of ancient stars that surrounds the galaxy like an ethereal shell. These stars are low in heavy elements, which tells astronomers they were born when the universe itself was young, before many generations of supernovae had enriched the cosmos. Their erratic orbits and diffuse distribution hint at the Milky Way's chaotic beginnings, when smaller protogalaxies collided and merged to form something greater. The halo is the galaxy's oldest memory, a record of its first steps toward becoming what we see today. Deeper in lies the bulge, the dense, golden heart of the Milky Way. Its stars are old, too, though slightly younger than those of the halo, and they trace the galaxy's adolescence when gas and gravity began to organize the chaos into something more symmetrical. Here, the evidence of growth and turmoil intertwines. Many of the bulge's stars were likely born in violent starbursts, triggered by early collisions. Their chemical signatures show a transition from primitive to complex, from a universe of hydrogen and helium to one filled with carbon, oxygen, and iron. The bulge is a fossil of transformation, recording the moment when the Milky Way became self-sustaining, capable of building new stars from its own ashes. Then comes the disk, where the spiral arms unfurl in luminous grace. It's the youngest layer, filled with gas and dust and ongoing creation. The stars here are rich in metals, evidence of billions of years of recycling through stellar births and deaths. Like sediment deposited in a flowing river, the disk holds the traces of every generation before it, each wave of star formation leaving behind a distinct chemical and spatial imprint. The thick disk, older and puffier, formed first. The thin disk, delicate and structured, came later, sculpted by the galaxy's maturing rotation. Together, they represent the living present of the Milky Way, still evolving as new stars ignite. Astronomers study these layers the way paleontologists study fossils, using light instead of rock, chemistry instead of bone. The color of a star tells its age. Its motion tells its origin. Its elemental makeup tells the story of the universe's enrichment. Each discovery is like unearthing a new stratum, adding depth to the galactic timeline. When you gaze at the Milky Way, you are seeing this record all at once. 13 billion years of formation layered across the sky. The faint stars at the edge are the halo's relics. The dense glow near the center is the bulge. The shimmering band stretching overhead is the disk, where new suns are still being born. It's a fossil record of light, written not in stone, but in the slow, patient language of starlight and time. When the Milky Way formed, the universe was still dark and new. Galaxies were rare then. Our own was among the first to find its rhythm. To imagine that, time is to imagine a cosmos still learning to shine. The Big Bang had happened only a few 100 million years earlier, and the universe was filled with a fog of hydrogen gas that absorbed most light. No galaxies glittered in the void. No starlight pierced the dark. But gravity was at work even then, gathering the first threads of matter into clumps that would one day become galaxies like ours. The Milky Way's earliest ancestors began as one of those faint condensations, an island of potential forming in an ocean of night. These first protogalaxies were small and chaotic, bound together more by chance than structure. Their stars, enormous and short-lived, burned with ferocity, lighting up the darkness for the first time. When they died, they spread the elements of life, carbon, oxygen, iron, into the surrounding gas. That enriched material became the foundation for everything to come: planets, moons, oceans, breath. Each new generation of stars built upon the ashes of the last, slowly transforming the universe from simplicity to complexity. When the Milky Way began to assemble, perhaps 13.6 billion years ago, the universe was less than a billion years old. Galaxies were closer together, still forming from the same primordial filaments of gas that stretched across the expanding cosmos. The Milky Way grew by merging with smaller systems, swallowing their stars and gas, layering itself piece by piece. In this way, it became one of the early architects of galactic form, a spiral emerging out of chaos, one of the first great patterns of order in a universe still finding its balance. The sky in that era would have looked utterly different. The first galaxies shone faint and red, their light stretched by the expanding fabric of space. Between them drifted immense clouds of neutral hydrogen, dimming and scattering the young starlight. There were no grand spirals yet, only compact, irregular clusters glowing weakly through the haze. But among them, the seed of our own galaxy already existed, gathering strength, preparing to spin. Today, with telescopes like James Webb, we can peer back into that ancient time. The light from those early galaxies has traveled for over 13 billion years to reach us, stretched and softened by cosmic expansion. Some of the faintest smudges Webb observes may be the Milky Way's distant cousins, galaxies forming alongside ours, kindled by the same primordial fire. To see them is to glimpse our own beginnings, the universe before memory, before structure, before us. It's humbling to know that when the Milky Way began, the universe was still learning to make galaxies at all. From that darkness, order emerged. From that simplicity, complexity arose. The Milky Way is a survivor of that first generation of cosmic architecture, proof that even in the infancy of time, the universe was already dreaming of light, structure, and the possibility of life that would one day look back and wonder how it all began. Each measurement, each model, points to the same conclusion. Our galaxy was born about 13.6 billion years ago, just after the universe itself began. It's a number that almost defies comprehension. 13.6 billion years, a span of time so vast that human language bends beneath it. And yet, through that incomprehensible expanse, the Milky Way has remained, growing, evolving. To speak of the galaxy's age is to tell the story of time itself, how matter found order, how light learned to endure, and how from the ashes of the first stars, something immense and alive was born. Astronomers have arrived at this age through a web of evidence as delicate as it is powerful. The oldest globular clusters, spherical groups of tens of thousands of stars that orbit the Milky Way's halo, are between 13 and 13.4 billion years old. Their stars, dim and metal-poor, carry the signature of the early universe, when heavy elements were scarce. Radioactive dating, using the slow decay of uranium and thorium within these ancient stars, tells a consistent story. They were formed just a few 100 million years after the Big Bang itself. Meanwhile, the galaxy's chemical composition reinforces the timeline. The abundance of certain isotopes, like iron and magnesium, shows how many generations of stars have come and gone. Too many, and the galaxy would be younger. Too few, and it would be older. The balance fits perfectly with a formation age of around 13.6 billion years. Even the Milky Way's dark matter halo, invisible but massive, seems to have coalesced around that same period, gathering the raw material from which the first stars would ignite. In this way, the galaxy becomes a bridge between the birth of the universe and the present moment. When the Milky Way formed, the cosmos itself was less than 1 billion years old. The first galaxies were still coming together, and the cosmic microwave background, the afterglow of creation, still shimmered with warmth. From that young, glowing expanse, gravity sculpted a structure that would last for eons. The Milky Way grew from a seed of density, pulling in gas, merging with its neighbors, and spinning itself into the luminous spiral we call home. To think of that timeline is to confront the scale of existence. Humanity has been here for less than the blink of a cosmic eye, our entire history compressed into a fraction of a single galactic rotation. Yet in that fraction, we've learned to measure the age of the very galaxy that birthed us, to count its years not with calendars, but with light, motion, and decay. And so, when scientists say the Milky Way is 13.6 billion years old, what they mean is this. Our galaxy was born from the same explosion that gave rise to everything, and it has carried that origin through time, like a memory made of stars. Every sunrise, every shadow, every thought is part of that unbroken story. A story that began when the universe itself was still young and has never truly stopped unfolding. 13.6 billion years. A number vast enough to contain every ancestor of light, every whisper of gravity, every dream of what might yet be. Our galaxy is not merely old, it is eternal in motion, a river of time flowing through itself, carrying the universe's first spark into forever. Globular clusters, dense spheres of ancient stars, are among the oldest objects in existence, shining today just as they did near the dawn of time. They drift around the Milky Way like silent sentinels, more than 150 of them, each a perfect sphere of light bound tightly by gravity. Some contain hundreds of thousands of stars packed into a region only a few dozen light-years wide, glowing like cosmic lanterns hanging in the dark. To gaze upon one is to look directly into the past, for these clusters are relics of the galaxy's earliest days, formed when the universe was young and the rules of creation were still being written. The stars inside globular clusters are old, so old that their chemical makeup reveals a time before the galaxy's spiral arms existed. They are metal-poor, meaning they formed before supernovae had scattered heavy elements like iron and carbon through the cosmos. Most are estimated to be between 12 and 13.4 billion years old, making them nearly as ancient as the Milky Way itself. They are the elders of the cosmos, their light a living record of the first era of star formation. Each cluster has its own unique story. Messier 13, the Great Hercules Cluster, contains more than 300,000 stars, its combined light visible even to the naked eye on a clear night. Omega Centauri, the largest in our galaxy, may not even be a true cluster at all, but the remnant core of a dwarf galaxy long ago devoured by the Milky Way. Its stars display a surprising range of ages and metallicities, suggesting that it once nurtured multiple generations of stellar birth before being stripped of its outer layers. And M15, a compact and brilliant cluster in Pegasus, may harbor a black hole at its heart, binding its stars together in a gravitational embrace older than Earth itself. For astronomers, globular clusters are more than beautiful. They are tools of timekeeping. By studying their stars' brightness, color, and chemical composition, scientists can estimate their ages with remarkable precision. They are like cosmic fossils, helping us date the formation of the Milky Way and trace how it assembled from smaller fragments. The oldest clusters show that our galaxy's story began astonishingly early, less than 1 billion years after the Big Bang. What's most haunting about these clusters is their endurance. While galaxies collide, stars explode, and planets are born and destroyed, globular clusters have remained largely unchanged for billions of years. Their stars move in slow, graceful orbits, bound by gravity and mutual history. If time itself had a heartbeat, it would pulse to the rhythm of these clusters, steady, ancient, serene. Look at one through a telescope, and you see a shimmering sphere that seems almost alive. Each point of light is a sun older than imagination, and together they create a glow that has not dimmed since the universe was young. They are the galaxy's elders, keepers of memory, holding within them the quiet wisdom of time. In their presence, the Milky Way remembers its childhood, the moment it first learned to shine. Radioactive isotopes like uranium and thorium decay with perfect regularity. Their presence in ancient stars acts like a galactic clock, ticking for billions of years. Time, in the galaxy's deepest sense, isn't kept by motion or memory, it's kept by decay. Long after stars fade and planets crumble, the slow disintegration of atoms continues, steady and precise. Each isotope carries within it a perfect rhythm, a built-in clock counting down the eons. Astronomers have learned to read those atomic beats like the hands of a cosmic watch, using them to measure the age of stars, clusters, and the galaxy itself. The principle is simple, though its implications stretch across eternity. Certain heavy elements, such as uranium-238 and thorium-232, are unstable. They decay into lighter elements at a fixed rate, known as their half-life. For uranium-238, that's about 4.5 billion years. For thorium-232, around 14 billion years. These timescales are nearly the same as the age of the universe, making them perfect tools for dating the oldest stars. When these isotopes were forged in the explosive deaths of the first supernovae and neutron star collisions, they began ticking, quietly marking time from the moment of their creation. By comparing how much uranium or thorium remains in a star to the amount of their stable decay products, like lead or hafnium, astronomers can estimate how long the process has been running. It's a method called nucleocosmochronology, and it works like carbon dating for the cosmos. Unlike the shifting motions of stars or the uncertain lifetimes of galaxies, radioactive decay never falters. It is the most patient form of timekeeping imaginable, steady, impartial, eternal. One of the most striking examples of this came from the discovery of the star CS 31082001, an ancient red giant located in the galactic halo. Its light revealed traces of uranium and thorium, atoms that had been decaying for over 13 billion years. By measuring their ratios, scientists determined that the star was almost as old as the Milky Way itself, born shortly after the first elements were scattered into space. In that one spectrum, they held proof that the galaxy's story began nearly at the dawn of time. These isotopic clocks are more than scientific curiosities. They are the galaxy's internal heartbeat. They keep time even in silence, even when stars no longer shine. Their decay is a whisper from the beginning, still audible in the faintest light of ancient stars. Each measurement of uranium or thorium is a dialogue across billions of years, connecting us with the universe's first moments of creation. And perhaps the most profound part is this. The same process that marks the age of stars also warms the hearts of planets. On Earth, the decay of uranium and thorium deep underground powers volcanic activity, shapes continents, and fuels the magnetic field that protects our atmosphere. The galaxy's great clock not only measures time, it sustains life within it. So when astronomers say they can read the galaxy's age, what they truly mean is that they can hear its ticking, a rhythm written into the atoms themselves. It's a pulse that began when the first stars exploded, a steady beat through cosmic history, still echoing now in the radioactive dust of distant suns. Astronomers can trace waves rippling through the galaxy's halo, vibrations left behind by collisions that happened more than 10 billion years ago. The halo, that vast and ghostly sphere surrounding the Milky Way, may look still and silent, but it is anything but static. Hidden in its immense emptiness are subtle motions, great tidal oscillations moving through the stars like invisible music. These ripples are not random. They are the long-lived echoes of ancient collisions, scars of encounters that once shook the entire galaxy to its core. Though billions of years have passed since those events, their rhythm continues, slow, graceful, and patient. The halo is composed mostly of old stars, globular clusters, and dark matter, a sprawling sphere that extends hundreds of thousands of light-years beyond the Milky Way's disk. To the eye, it appears empty. But when astronomers plot the positions and velocities of its stars, a hidden pattern emerges. Waves, shells, and arcs that reveal a story of motion. Some stars move slightly faster, some slower, some higher above the galactic plane, as if stirred by a hand that passed long ago. These are the galaxy's gravitational ripples, remnants of past mergers that reshaped its form. One of the most prominent of these patterns is called the Gaia sausage, a vast, elongated structure of stars discovered through the European Space Agency's Gaia mission. It's the remnant of a dwarf galaxy that collided with the Milky Way roughly 10 billion years ago. When it was absorbed, it didn't vanish quietly. It sent ripples through the halo, like a stone dropped into water. Those vibrations still move through the stars today, forming waves that astronomers can map in 3 dimensions. Another ripple, known as the Monoceros ring, wraps around the outer edge of the Milky Way's disk, a looping arc of stars that may be the remains of another ancient collision. It's as though the halo is breathing, expanding, and contracting in slow motion. Each oscillation carries memory. Each movement a record of a time when our galaxy was still assembling itself, feeding on its smaller neighbors in a cosmic act of creation. By measuring these motions, scientists can reconstruct the events that caused them. They can estimate how massive the colliding galaxies were, when they fell in, and how they reshaped the Milky Way's structure. In doing so, astronomers have learned that our galaxy's smooth, spiral form is the result not of peace, but of ancient turbulence, a choreography born from chaos. The beauty of these halo waves is in their endurance. Even after 10 billion years, they have not faded completely. The stars still remember the touch of those old collisions, still sway to their rhythm. It's a form of cosmic memory written not in light, but in motion, an echo so vast that it takes hundreds of millions of years for a single cycle to complete. To look into the halo is to listen to the galaxy's slow heartbeat, to hear, in the quiet shimmer of old stars, the lingering pulse of creation itself. Its outermost stars still sing the song of its birth, a music too slow for our ears but perfectly in tune with the timeless rhythm of the cosmos. The Milky Way isn't alone. It's part of a cosmic network, threads of galaxies woven together since the universe's earliest dawn. If you could step outside the universe and look back, you wouldn't see a random scatter of galaxies drifting through emptiness. You'd see something astonishing, a web, a vast, luminous structure stretching across billions of light years, woven from filaments of matter and energy. Along those filaments, galaxies cluster like dewdrops on an invisible thread, bound together by gravity's gentle persistence. The Milky Way is one of those droplets, glittering on a strand of cosmic silk that connects it to everything else. This cosmic web was born in the universe's first billion years. Tiny fluctuations in the density of the primordial plasma, ripples in the afterglow of the Big Bang, grew under the pull of gravity. Over time, the denser regions collapsed into long filaments of dark matter and gas, while the emptier regions expanded into vast cosmic voids. Where filaments intersected, galaxies formed. Our Milky Way sits at one of those intersections, in a region astronomers call the local sheet, surrounded by neighboring galaxies like Andromeda, Triangulum, and dozens of smaller dwarfs. Together, they make up the local group, a small cluster adrift in one of the web's shimmering threads. Beyond the local group lies the Virgo supercluster, a sprawling congregation of thousands of galaxies bound together across more than 100 million light-years. But even that immense structure is only one filament in a larger tapestry. The Laniakea supercluster, a gravitational basin containing more than 100,000 galaxies, all flowing along the same vast currents of matter. The Milky Way, Andromeda, and their companions move together through this region like particles suspended in a cosmic river, drawn by the subtle contours of gravity on unimaginable scales. The web itself is mostly invisible, composed of dark matter that neither emits nor absorbs light. Yet its presence shapes everything we can see. Gas follows the dark matter's scaffolding, cooling and condensing into galaxies. Light bends as it passes through its gravitational wells, revealing its intricate filaments to astronomers through a phenomenon called gravitational lensing. In recent years, observatories like the Sloan Digital Sky Survey and simulations such as Illustris and Millennium have mapped this structure in exquisite detail, showing us that the universe is not chaotic, but exquisitely organized, connected at every scale. The Milky Way's age, 13.6 billion years, means it has existed for almost as long as the web itself. It has grown, collided, and evolved within this network, feeding from its filaments and sending out its own matter in return. In a sense, our galaxy breathes with the cosmos, expanding and contracting in harmony with the great structure it inhabits. To grasp this is to feel a kind of cosmic kinship. The stars above you, the atoms within you, the galaxies beyond sight, all are part of one vast, interlinked fabric. Gravity is the thread, time the loom, and light the pattern that reveals the whole. The Milky Way may seem solitary when we gaze up at it from Earth, but it is not alone. It is one bright bead on the infinite necklace of creation, a single note in the quiet, eternal symphony of the galactic web. Some stars appear older than the galaxy itself, a puzzle that forces scientists to rethink everything they know about cosmic chronology. It sounds impossible, even absurd. How could a star be older than the galaxy it belongs to? And yet, that's exactly what some observations suggest. Hidden among the Milky Way's oldest populations are stars whose estimated ages push the very limits of the universe's timeline. Some appearing to have formed before the galaxy did, perhaps even before galaxies existed at all. These stellar enigmas are cosmic paradoxes, relics that defy our neat understanding of when and how the Milky Way began. One such mystery star is HD 140283, often called the Methuselah star. Located just 190 light-years away, it's a dim, ancient subgiant drifting quietly through the galactic halo. When scientists analyzed its light, they discovered it contained almost no heavy elements, just traces of oxygen and iron. Using models of stellar evolution, its age was calculated at around 14.5 billion years, older than the universe itself, which is 13.8 billion years old. Though later refinements brought that estimate slightly down to about 13.2 billion, the paradox remains. This star was born at the very dawn of time, possibly from material enriched by only the first generation of supernovae. Stars like HD 140283 reveal the exquisite difficulty of measuring cosmic ages. Estimating how long a star has lived requires understanding the physics of nuclear fusion, the composition of its atmosphere, and the subtle ways in which heavy elements alter its brightness and temperature. Even a tiny uncertainty, a 1% error in temperature, a small miscalculation in opacity, can shift an age estimate by hundreds of millions of years. These discrepancies remind astronomers how fragile our sense of time becomes when stretched across the universe's history. But the paradox may tell a deeper story. Perhaps these older-than-the-galaxy stars are immigrants, formed in smaller, independent systems that predate the Milky Way and were later absorbed into its halo. The Milky Way grew by consuming such ancient dwarfs, each bringing in its own relic stars. If so, then the Methuselah star and its kin are not contradictions. They're survivors. They were born in the universe's first billion years, long before the Milky Way took shape, and they now orbit within it as living fossils from a forgotten age. Another possibility is that our cosmic clocks need recalibration. Stellar physics continues to evolve. New data from the Gaia mission has refined distances and brightness measurements for billions of stars, improving our ability to age them accurately. These efforts are helping close the gap between theory and observation, but they also show how much of the universe's story remains unwritten. The age paradox is not a failure of science, it's an invitation to wonder. It reminds us that time, in the cosmos, is not a simple line but a tangled web of origins, collisions, and continuities. Some stars carry the memory of galaxies long vanished, others burn with the freshness of creation. Together, they create a timeline that is not chronological but poetic, a symphony of beginnings that overlap and resonate through the ages. In the end, the paradox may not be that some stars are too old, but that the universe is too young to contain all its memories. The Methuselah star does not defy time, it defines it, holding within its faint light the first whispers of everything that would one day become us. At 13.6 billion years, our galaxy is neither young nor dying. It's in its cosmic middle age, still creating stars, still learning what it means to exist. If galaxies could think, the Milky Way would be in the reflective stage of life, the age when one looks back on origins with wisdom, yet still looks forward with curiosity. Born in the fires of the early universe, it has survived collisions, grown its spiral arms, and forged countless generations of stars. Now, it spins with quiet confidence, a mature system that has found its rhythm among the stars. The frenzy of its youth has softened into balance. Creation still happens, but more gently now, measured, patient, like a breath between epochs. In its early days, the Milky Way was chaotic and hungry. Gas clouds collided, dwarf galaxies were devoured, and starbursts flared across the galactic core. But that restless energy eventually gave way to order. The disk settled, the spiral arms formed, and the central bulge grew luminous with ancient stars. Now, the galaxy creates new suns at a rate of about 1 or 2 per year, a far cry from the tens or hundreds it once birthed in its adolescence. Yet this steady pace is sustainable, like a heart that has learned to beat calmly after ages of excitement. Across the spiral arms, stellar nurseries still glow. The Orion Nebula, the Carina Nebula, the Eagle Nebula, all reminders that the Milky Way has not forgotten how to begin again. But elsewhere, in the quiet outskirts and aging halo, old stars drift like embers fading in the night. Together they paint a portrait of a galaxy that is not static, but balanced, half in creation, half in memory. Our own sun was born during this era of quiet maturity. By the time it formed 4.6 billion years ago, the Milky Way had already lived through 2/3 of its history. The raw chaos of the early cosmos had passed, leaving behind a stable environment where complex chemistry and eventually life could flourish. The galaxy's middle age made us possible. Its calm was our cradle. And yet, even now, the Milky Way's story continues to evolve. Its spiral arms are still slowly reshaping. Its halo still ripples with the echoes of ancient collisions. The Andromeda galaxy approaches from across the void, promising a grand merger billions of years from now, a kind of renewal through transformation. Midlife, after all, is not the end of motion, it's the beginning of reflection. Astronomers call this period the galactic main sequence, the long, stable phase in which a galaxy maintains its structure, forms stars, and finds equilibrium between birth and decay. For the Milky Way, that balance could last another tens of billions of years, long after our sun is gone. Eventually, star formation will slow to a whisper, and the galaxy will fade into a sea of red dwarfs and white embers. But for now, it is vibrant, spinning, shining, alive. The Milky Way's middle age is a kind of cosmic grace. It's the quiet between the explosions, the peace earned through endurance. In its arcs of light, we can read a story of survival, a galaxy that has weathered the storms of creation and emerged serene, still curious, still composing its song in the darkness. It is old enough to remember the beginning, yet young enough to imagine what comes next. In another 100 billion years, our galaxy's light will fade as star formation slows. The Milky Way will grow quieter, but never forgotten. Nothing in the universe lasts forever, not even the stars. Though the Milky Way feels eternal to us, its glow is part of a long, unfolding cycle that will one day come to rest. Right now, our galaxy still hums with energy. Stars are being born, others are dying, nebulae pulse with ultraviolet light. But in the far future, this rhythm will slow. The vast clouds of gas and dust that fuel new suns will be used up or blown away. The spiral arms will dim, their brilliant blue-white stars replaced by older, redder ones. Creation will yield to reflection, and the Milky Way will enter its twilight. Astronomers call this distant era the degenerate age of the universe, a time when galaxies stop giving birth to new stars and instead live quietly among the remnants of their past. In 100 billion years, the Milky Way, merged long ago with Andromeda, will likely be an enormous elliptical galaxy filled with aging red dwarfs and cooling white dwarfs. Its brilliant spiral form will be gone, replaced by a smooth, golden glow. Most of its luminous matter will have dimmed to embers, but its story will still linger in the orbits of its stars, in the gentle arcs of light, still circling its invisible center. And even in that quiet future, the galaxy will not be truly dead. Red dwarf stars, the smallest and most enduring, can live for trillions of years, outlasting everything we know. Their soft, ruddy light will keep glowing across the darkness, illuminating whatever remains of our cosmic home. Planets may still circle them, frozen but steadfast, tracing paths through a universe that has long since grown cold. The Milky Way's last stars will die not in a blaze, but in silence, a slow exhale at the end of an age. By then, the night sky, if anyone were still there to see it, would look profoundly different. The universe's expansion will have carried other galaxies so far away that their light can no longer reach us. The Milky Way's descendants will exist in solitude, an island of fading starlight adrift in an infinite dark. Yet within that darkness, memory will remain. The metals forged in our galaxy's first stars will still exist in its last ones, the same atoms that once made oceans, forests, and eyes that gazed upward will still drift through its dust. Perhaps that is the true legacy of the Milky Way, not its brightness, but its endurance. It has already lived for nearly the entire history of the cosmos, and even as time stretches beyond imagining, traces of its light will persist. In the farthest future, when galaxies grow faint and space itself cools towards silence, the Milky Way's story will still echo in the particles it set free, in the starlight still crossing the void, in the atoms that once dreamed within it. The future of our galaxy is not an ending, but a fading note, a long, quiet sustain that hums through eternity. And though the light will dim, the memory will not. The Milky Way will remain, a whisper written in gravity, a story that time itself could not forget. Eventually, even galaxies age beyond beauty. Hydrogen runs dry, stars die, and only the memory of light remains, a whisper across eternal night. Imagine the universe not as it is now, but as it will be when all clocks have fallen silent. The stars are gone, the galaxies dim, and what was once a glittering cosmos has settled into stillness. The Milky Way, merged, evolved, and transformed, will have long since exhausted its fuel for creation. Its luminous arms will be nothing more than faint echoes, a halo of fading embers drifting through infinite dark. Every star that once burned bright will have lived its life, expanded, cooled, and gone dark. Time itself will stretch thin, and what remains will be quiet beyond comprehension. This is the farthest future astronomers can imagine, the heat death of the universe. It's not a violent end, but a slow unraveling, a cosmic sigh. Over trillions upon trillions of years, all the hydrogen and helium, the building blocks of stars, will be consumed. Black holes will be the last engines of energy, devouring what remains of matter before they, too, evaporate through Hawking radiation. When that happens, not even gravity will hold sway. The universe will become a thin mist of particles drifting forever through the infinite. But before that silence, there will be an age of quiet beauty. Red dwarfs, the smallest and longest-lived stars, will glow softly for trillions of years, outlasting every other kind of star. Around them, perhaps, will orbit lonely planets, remnants of solar systems that once thrived. To any eye that could see, the night sky would no longer sparkle. Instead, it would pulse faintly with the slow heartbeat of dying stars. The light will not end abruptly, it will fade, gently, as if the cosmos itself were falling asleep. When time runs out, there will be no one left to measure it. The word age will lose meaning. Entropy, the tendency of all things to drift toward disorder, will have claimed even the galaxies. Energy will be evenly spread across an ever-expanding void. And yet, somewhere within that silence, the memory of what once was will persist. The particles forged in the Milky Way's stars, the same atoms that once made up oceans, clouds, and consciousness, will still exist, scattered through the darkness. In that sense, the end of time is not the end of meaning. The story of the galaxy, of life, of light, will have already been written into the fabric of the cosmos. It will exist not in motion or flame, but in residue, in the quiet fact that, for a brief eternity, the universe created something that could see itself. When time runs out, there will be no stars to look back, no minds to wonder, no galaxies to hold shape. But the memory of light, the trace of what once burned, shimmered, and dreamed, will linger like the faintest note of a song that never truly ended. And perhaps that is what eternity really is. Not endless time, but the final stillness after everything that could shine has shone. A silence vast enough to hold the memory of all light that ever was. To measure the Milky Way's age is to measure ourselves. For we are not apart from it, we are its children, born from its dust, still glowing with its memory. When we look up at the Milky Way, we are not simply observing something distant, we are looking into a mirror made of light and time. Every atom in our bodies, every molecule that composes us, was once part of this ancient spiral story. We carry its chemistry, its history, its heartbeat. The galaxy is not just our home, it is our origin, our inheritance, our reflection. To understand how old it is, how patiently it has turned in the dark, is to glimpse the depth of our own belonging to the universe. For 13.6 billion years, the Milky Way has been writing its autobiography in starlight. Each generation of stars added a new chapter, each explosion a new punctuation mark. From the first halo stars forged from primordial gas to the young, blue suns still forming in its spiral arms, the galaxy's history has been one of continuity, a great, unbroken conversation between matter and time. When we trace that story backward, through the fossils of old stars, through the ripples of the halo and the chemical fingerprints of ancient light. We are tracing the lineage of ourselves. We are the latest sentence in a story that began before galaxies had names, before time had shape. The tools we use to measure the galaxy's age, radioactive isotopes, stellar motion, the faint glow of distant clusters, are, in truth, instruments for measuring memory. They reveal that creation was not a singular moment, but a long unfolding, a slow evolution from simplicity to complexity, from darkness to awareness. The galaxy's clock ticks in elements and orbits, but its meaning beats within us. Every thought, every breath, every act of wonder is the Milky Way remembering itself through us. And when we ask, how old is our galaxy? What we're really asking is, the answer, 13.5 billion years, means that the atoms in your body were there when the first stars ignited. It means that the calcium in your bones was born in the galaxy's childhood. The iron in your blood carries the memory of its adolescence, and the oxygen you breathe is the breath of its long, ongoing life. To measure the Milky Way's age is not to mark its distance from us, it's to acknowledge our place within it. We are part of the same chronology, the same unfolding. The light that shaped the galaxy shaped us too. And so, as you gaze into the river of stars tonight, remember that you are seeing yourself, not in reflection, but in continuation. You are the galaxy, aware of its own age, its own endurance, its own light, and long after your breath has faded, after the stars themselves have dimmed, the memory of this connection will remain, written across eternity, glowing softly in the mirror of ages. The stars we trace tonight are not strangers but family, fossils of fire and dust that together write the Milky Way's long, patient biography. We followed ancient halo stars and the crowded bulge, read the chemical clocks hidden in iron and uranium, and listened to the slow music of motions that marks an age, roughly 13.5 billion years, almost as old as the universe that cradled it. We watched how galaxies were born in light and violence, how tiny islands of stars were devoured and folded into a grand spiral, how stardust became oceans and, eventually, us. Remember that every atom in you once glowed in some long-dead star. Every breath is a passing of that memory. The Milky Way's age is not just a number. It is a guarantee of time enough, time for complexity, for chance, for gardens of chemistry to become minds that can look back and wonder. It is a reminder that continuity and change can live together. New stars are still being born, even as ancient clusters keep vigil from the halo. In the future, we will meet Andromeda, two old spirals dancing toward a shared tomorrow. For now, we rest beneath their combined light. If tonight you feel small, let that smallness be soft rather than faint. Being small in a galaxy this old is to be part of a patient story that stretches from the first light to the hush between heartbeats. Be grateful for the simple miracle of being here to listen, to exist inside a galaxy that has carried its history for billions of years so we could awake and ask our questions. Take a slow breath. Let the image of the river of stars carry you away, quiet, steady, timeless. You are stardust, tender, curious, luminous. Sleep now beneath the Milky Way's slow turning. Let its age be your lullaby. Good night.